ELS has been updated with a new calculation approach using absorbing boundaries and damping to simulate an infinite domain, significantly improving accuracy in ground impact analysis. The user applies the load at the center of the model in order to observe how stress waves propagate through the ground. The model you see here consists of a cylindrical column with a mesh that gradually increases in size outward, using an expansion ratio of 1.1. This is an elastic model, and the load is applied at the center. In this problem, stress waves travel through the ground at a speed of roughly 1,000 feet per second, depending on material properties. This speed is determined by the square root of the elastic modulus divided by the density. Because of this high propagation speed, the wave quickly reaches the model boundary. In our case, the boundary is located about 500 feet away from the structure. This means that within about 1 second, the wave reaches the boundary, reflects back, and interferes with the input signal. As a result, any simulation lasting longer than about 1 second becomes distorted by artificial reflections, because in reality, the soil extends to infinite distance. To work around this limitation, some users choose to truncate the loading history. Instead of applying the full impact, the user would extract only a portion of the load and use that as input. While this approach works, it is not ideal since it prevents us from modeling long impact durations. One of the available features in ELS to address this challenge is the use of absorbing boundaries based on Lismer damping. These transmitting boundaries are applied along the sides of the cylindrical model and at the base. Their purpose is to absorb outgoing wave energy, effectively simulating an infinite domain rather than a finite one. With these absorbing boundaries in place, waves no longer reflect back into the model. Instead, they dissipate naturally at the boundaries. This allows us to apply the full load history without worrying about artificial reflections. Let's take a look at the loading scenario. Here, we are using the complete impact history. This impact history is usually obtained from a separate problem where the user studies a falling object or structure hitting the ground. This can be done using the synchronous loading tool in ELS, which is described in another video available in the description. The load begins at 0, increases during impact, and eventually reaches a constant value which is equal to the static weight of the falling structure as it settles onto the ground. The full duration of this loading is about 10 seconds. With the transmitting boundary modeling, the user can apply the entire loading history. What is particularly interesting is that the results validate our earlier assumptions. When we compare simulations using the truncated load versus the full load, we find that the peak vertical velocity is essentially the same, about 9 millimeters per second. This confirms that our earlier simplified approach was actually quite accurate. This top chart is showing the vibration velocity for 4 elements, while the bottom chart shows that the weight of the structure is 16,000 kips, and 38,000 kips is the maximum impact. Another important observation is that when the load becomes constant towards the end of the simulation, the vertical velocity drops to nearly 0. This is exactly what we expect physically, since a constant force does not produce additional acceleration once equilibrium is reached. The second conclusion is that the truncation method, where the user only considers the duration of the peak load instead of the entire loading history, was an acceptable approximation for this case. To support the weight of the structure, we have static springs at the base of the model to support the vertical reaction. These springs maintain stability at the end of the simulation, when we reach the static stage. Now, let's take a look at the animation. At the beginning, there is no load. Then, as the impact occurs, stress waves propagate outward from the center. As these waves reach the boundaries, they are absorbed rather than reflected. The system responds with a peak during the major impact event, followed by smaller oscillations that gradually dissipate. Eventually, the system settles and the ground motion diminishes to nearly 0. This advancement is significant for several reasons. First, it allows us to simulate the full impact event with greater realism. Second, it enables side-by-side visualization of structural collapse and ground response. Finally, it opens the possibility of running parallel simulations where real-time impact forces are applied directly to the ground model.